252 million years ago, on a shoreline that no longer exists, the sea was beginning to change color. Not green, not blue, but a slow, bruised purple, creeping outward from the horizon like ink pressed into wet paper. Nothing visible was killing it. No meteor had fallen, no fires burned along the coast. The air was warm, and the wind moved gently over the water, carrying nothing more than the faint metallic smell of sulfur. And yet, beneath the waves, 96 of every 100 living things were already dying. They did not know it. They could not have known it. They were trilobites and brachiopods and vast silent forests of sea lilies fanning in currents that would soon stop moving. They were corals older than language and fish with armored plates and tiny shelled creatures drifting in clouds so thick the sunlight barely reached the floor. Their world had lasted, in something close to its present shape, for almost 300 million years, and it had 60,000 years left. This is the story of how the largest ocean the Earth has ever seen forgot how to breathe. With no outside enemy and no single wound, drifted quietly into the deadliest silence in its entire history. It is called now the Great Dying. And what follows is a slow reconstruction in images and numbers and what the stone itself remembers of what it was to be there in the moment the water turned. To understand what was lost, you have to imagine what was there. 252 million years ago, all of the continents of Earth had drifted together into a single enormous land. It was called Pangaea, one land, wrapping itself around the middle of the world like a fist holding the sea inside it. On the other side of Pangaea stretched a single ocean so vast that if you stood on any of its shores and sailed outward, you could travel for months without ever seeing land again. This ocean had a name too, Panthalassa. It covered roughly 70% of the planet, and it was one of the richest places life has ever produced. In its shallow shelves along the margins of Pangaea, the water was warm and clear and heavy with oxygen. Light reached down through tens of meters, illuminating vast fields of calcium carbonate reefs built by organisms most of us will never hear the names of. Tabulate corals, rugose corals, bryozoans. These reefs were not like modern coral reefs. They were older architectures layered with sponges and stromatolites, structures that had been refined across 300 million years of trial and patience. And in between them, life moved in shapes that have no living relatives. Perhaps the most famous of the lost ones were already old by the Permian. They had existed for more than 250 million years by this point, a lineage longer than the entire age of mammals. They walked the sea floor on hundreds of small legs, their armored bodies segmented like living jewelry, their eyes made of calcite crystals that focused light in ways no modern eye can. There were still dozens of species in the late Permian, smaller than their ancestors, quieter than in their ancient heyday, but persistent. They had survived 3 earlier mass extinctions. They would not survive the next one. Above them drifted ammonoids, coiled shelled predators related distantly to today's octopus and nautilus. Below them, in the sediment, brachiopods opened and closed their paired shells in a rhythm that had not changed in 500 million years. Single-celled foraminifera the size of grains of rice covered the sea floor in such numbers that their fossil shells now make up entire limestone beds across Texas, China, and the Russian Urals. Crinoids, the sea lilies, fanned in currents, their long segmented stalks tethering them to rocks, their feathered arms filtering microscopic food from the water. Some fossils of those crinoid meadows stretch across kilometers of ancient sea floor. Entire pastures of them preserved in stone. The air above was thick with moisture and warmer than today. Oxygen levels in the atmosphere had peaked some tens of millions of years earlier, during the Carboniferous, but they were still high. Global temperatures were a few degrees warmer than in our present, There were no polar ice caps of any significant size. Seasons were soft, shaped more by geography than by cold. Forests of seed ferns and conifer ancestors covered the margins of Pangaea. Across the dry continental interior, new kinds of animals were taking hold. The therapsids, mammal-like reptiles that walked upright and bore young that were, in some ways, very close to what mammals would eventually become. The world was not simple. It was not primitive. It was not, as some imagine, waiting to be replaced by something better. It was a deeply mature ecosystem, refined across hundreds of millions of years, as layered and precise as a modern one. The creatures in it were not stepping stones. By every measure that matters, finished. They were exactly what the Permian had made of them. Some of their lineages had been evolving without catastrophic interruption since before there were trees, since before there were insects, since before there were, in any meaningful way, plants on land. And the sea, the Panthelastic Sea stretching unbroken around the far hemisphere of Pangaea, held the greatest share of that finished life. It was not full of noise, because sound underwater carried differently than in a saltier, slightly warmer ocean. But it was full in every sense. You could not have drawn a cubic meter of water anywhere near a shelf without pulling up dozens of tiny living things. The end of this world was not unimaginable, but no one, if they could have imagined, would have believed it was close. 300 million years had built this, and the first thing to die, when the dying began, would not be a creature at all. The earliest sign of what was coming is not in the bones, it is in the chemistry of the stone. Working through rock sequences that span the boundary between the Permian and the Triassic, the so-called PT boundary, have learned to read the changes in atoms the way you might read changes in a voice. Before the bodies vanish, the ratios of carbon isotopes in the sediment begin, quietly, to shift. The ratio of carbon-12 to carbon-13 is one of the most sensitive recorders of planetary life. Living things, breathing things prefer the lighter isotope. So as long as the biosphere is healthy and pulling carbon out of the air, the ocean sediment is enriched in the heavier form. When life starts to fail, or when an enormous quantity of light carbon suddenly enters the system from outside, from volcanoes, from burning organic matter, that balance begins to slip. In the rocks that record the late Permian, beginning some tens of thousands of years before the main extinction pulse, that balance begins to slip. It is not a dramatic slip. Not yet. It is a whisper. In the sections at Meishan, in southern China, one of the most carefully studied records of the PT boundary in the world, you can see the carbon isotope curve begin to dip. A few thousandths of a percent, a number so small that in any other rock, it might mean nothing. But layered through meters of mudstone, repeated across continents, it tells the same story everywhere at the same time. Something was beginning to breathe out too much carbon. Something was changing the composition of the sky. And then the smaller creatures began to disappear. Not the big ones. Not yet. The first to go were the most vulnerable, the small, specialized deep-water organisms that had narrower temperature tolerances. Those rice grain-sized foraminifera that had once paved the sea floor began to thin out. Certain radiolarians vanished from the deep-water sediments. Corals in the reefs that were closest to the equator began at the edges to bleach and die. In any single layer of stone would have looked like a catastrophe. If you had been there, walking a shoreline in some late Permian afternoon, you would not have seen anything wrong. You would not have been able to taste it in the air. You would not have noticed that a few species of plankton were missing from the water because you would never have seen them in the first place. But the stone remembers. And if you follow the layers upward through the last 10,000 years of the Permian, the whispers become louder. The carbon curve dips further. Oxygen isotopes, which record ocean temperature, begin to rise. The sea is warming. A degree, 2, 3. slowly at first. The distribution of certain species starts to shift polewards as the tropics become slightly too hot for them, just as species today are shifting polewards in the face of our own warming. Reef growth in the shallow tropics begins to stall. The great trilobites, already rare, become rarer still. If you had been a geologist living in the late Permian with all of our modern instruments, you might have noticed. You might have been uneasy. You would not probably have called it a crisis. The Earth has always fluctuated. Temperatures rise and fall. Oceans warm and cool. The planet has had pulses of volcanism before, brief dark seasons, short sharp extinctions. It had always, before, returned to itself. This time, it would not. Because far to the north, beneath a continental plate that sat where today we find the cold, quiet, mostly empty plains of Siberia, something enormous was beginning to stir. It had been building for millions of years, a plume of superheated rock rising from deep within the mantle, pushing slowly against the underside of the crust. You could not have seen it from the surface. You could not have felt it. The first tremors were still far away. But in the deep earth, a pressure was reaching a threshold, and when it crossed that threshold, it would not release the way ordinary volcanoes release, in a mountain, in a single cone, in an eruption of days or weeks. It would release the way flood basalts release, across thousands of kilometers, for hundreds of thousands of years. The first thing to die, when the dying began, was the sky. When the Siberian traps began to erupt, they did not erupt the way we think of eruptions. There was no single mountain. There was no single day. There was, instead, a slow, enormous opening of the crust across a region larger than most modern countries, stretching across what is now western Siberia. The eruptions began, the best current dating tells us, roughly 250,000 years before the main extinction pulse. They continued in pulses for roughly 2 million years, and in that time, they released an amount of molten rock that is difficult to describe without numbers that sound unreal. 4 million cubic kilometers of basalt. 4 million. If you tried to spread that much lava across the continental United States, it would cover it to a depth of nearly half a kilometer. If you spread it across Europe, the same. It is an amount of material greater than every mountain range humans have ever climbed combined. It flowed in places in river-like sheets hundreds of kilometers long, advancing over landscapes at the pace of a walking person, slow enough for animals to flee, large enough that the fleeing never stopped. And the basalt itself, the glowing river, was only part of what mattered. The rest of what mattered was in the gas. When molten rock rises from the mantle and cools at the surface, it releases into the atmosphere an enormous volume of dissolved volatiles. Carbon dioxide, sulfur dioxide, hydrogen fluoride, chlorine, methane sometimes, where the magma passes through organic sediments. In the case of the Siberian traps, the magma did pass through organic sediments. It rose, in places, through enormous buried coal seams and thick layers of hydrocarbon-rich rock laid down across the Carboniferous and the earlier Permian. And when it met those layers, it cooked them. It superheated them. It released, along with its own volcanic gases, the stored carbon of an entire earlier age of forests. The total amount of carbon dioxide injected into the Permian atmosphere in those 2 million years is estimated, in different models, at anywhere between 30,000 and 100,000 gigatons. For comparison, the entire fossil fuel carbon output of the modern human industrial age, from the beginning of the 18th century to the present, is somewhere around 2,000 gigatons. The Siberian traps released, depending on which estimate you trust, between 15 and 50 times that much. They simply took longer to do it. The atmosphere responded the way atmospheres must respond when the chemistry of the air is changed. The tropical oceans, which had been perhaps 25 degrees Celsius at the surface, began to climb. 1 degree, 2, 5. By the time the extinction pulse reached its peak, sea surface temperatures in the equatorial Panthalassic Ocean had risen by an estimated 10 degrees. Let that stand for a moment without being translated into another number. An ocean that had held its temperature roughly steady for tens of millions of years warmed, across a few tens of thousands of years, by more than the difference between a pleasant summer and a summer that would kill you if you stood in it too long. And the warming was worse at depth. Because the thing people often do not understand about the ocean, the thing that turns out to matter more than almost anything else in this story, is that the ocean does not mix the way you might imagine. The ocean is layered. Warm surface water, lighter than cold deep water, floats on top. Between them lies a boundary, a temperature gradient called the thermocline, which resists mixing. Below the thermocline, the deep ocean is quiet, slow, and cold. It receives its oxygen primarily from one place, from the polar regions, where very cold, very dense water sinks and carries dissolved oxygen down into the abyss, where it circulates slowly for hundreds or thousands of years before returning to the surface. This circulation, this slow breath of the planet, is what keeps the deep ocean alive. It is how the deep floor receives its dissolved oxygen. It is how life, anywhere below the sunlit surface, is able to exist at all. When you warm the surface ocean, you do two things. First, warm water holds less dissolved oxygen than cold water. This is a simple matter of gas solubility. The same reason a cold glass of water holds its fizz longer than a warm one, so the surface ocean's oxygen content falls. Second, and more important, warming strengthens the thermocline. The surface, now warmer and therefore lighter still, mixes less easily with the deep. The sinking of cold polar water slows because the poles themselves have warmed. The slow breath of the planet weakens. The deep ocean, which depends on that breath, begins to run out of oxygen. Oceanographers call this state anoxia, when the dissolved oxygen in a body of water drops below a threshold at which most animals can survive. The water has become anoxic. And once anoxia begins to spread, something else starts to happen in the water chemistry. Something much stranger and much worse. In water that still has oxygen, bacteria that break down organic matter do so aerobically. They use the dissolved oxygen, and the products of their work are carbon dioxide and water. Familiar, harmless enough. But in water without oxygen, a different family of bacteria takes over. Sulfate-reducing bacteria. They do not use oxygen. They use dissolved sulfate, the sulfur-rich salts that are dissolved naturally in enormous quantities in seawater. And in the course of their metabolism, they produce, as a waste product, a gas that any of us would recognize instantly, because a very small amount of it is what gives rotten eggs their smell. Hydrogen sulfide. In ordinary, oxygenated seawater, hydrogen sulfide cannot build up. It reacts immediately with dissolved oxygen and falls out of the water as harmless sulfate minerals. But in deep anoxic water with no oxygen present, it accumulates millimole by millimole, parts per million by parts per million. There is, in every anoxic body of water, a boundary called the chemocline. It is a layer, sometimes sharp, sometimes gradual, below which the water is poisoned by hydrogen sulfide and above which the water is still healthy. The chemocline in the modern Black Sea, for example, sits at roughly 150 meters below the surface. Above it, you can swim, you can dive, you can sail. Below it, nothing larger than a few resistant bacteria can survive. The Black Sea is the largest anoxic basin on the planet today, and it is tiny compared to what the late Permian oceans became. Because as the Permian warming continued, as the Siberian traps kept erupting, as the carbon dioxide kept rising, as the surface ocean kept losing oxygen, The chemocline in the Panthalassic Ocean began slowly to rise. 100 meters, 200, 300. Over thousands of years, the line between healthy and poisoned water lifted itself upward through the water column, toward the continental shelves, toward the light. The organisms living just above it had no way to escape. When the chemocline overtook them, they simply stopped breathing. And the zone of death expanded, first outward along the deep margins, then upward into the shallows where life had been densest. Reef after reef, meadow after meadow, the ecosystems of the shelf began to suffocate from below. If you had been able to stand somewhere above a late Permian reef and watch what happened, you would not have seen much. You would not have seen fire. You would not have seen blood. You would have seen, over tens of centuries, the creatures of the reef simply become fewer. You would have seen their bodies drift, uneaten, because the scavengers were dying too. You would have seen the water faintly lose its clarity as oxygen-dependent filter feeders failed, and the microscopic life that stained the water began to change. You would have seen the reef turn gray, and you would have smelled on the wind coming off the shore the first slow trace of what was rising. The water did not turn purple everywhere at once, but wherever the chemocline reached the sunlit zone, the color came. It came from a particular family of bacteria, one that only thrives in a very specific, very unusual condition where light and hydrogen sulfide meet. In the modern world, you can find them in small quantities, in certain meromictic lakes, in a few isolated marine basins, in hot springs. They are called purple sulfur bacteria. They are photosynthetic, like plants, but they do not use water as their hydrogen source. They use hydrogen sulfide. They split the molecule, use the hydrogen for the same chemistry that plants perform with water, and release not oxygen, but tiny particles of elemental sulfur as a waste product. Their pigments, in visible light, appear a deep dusty violet. In dense concentrations, they stain the water the color of a bruise. For the vast majority of Earth's history since the rise of oxygen, these bacteria have been marginal organisms. They live in the thin, narrow band where sulfide and light overlap, and in a healthy ocean, that band is pressed down so deep into darkness that there is almost no light for them to use. But as the late Permian chemocline rose and the sulfide-rich water climbed closer to the surface, the band of overlap expanded, and expanded, and expanded. There is geochemical evidence now that in shallow shelf environments across the PT boundary, purple sulfur bacteria bloomed in quantities unlike anything before or since. We find their chemical signatures, specific molecular fossils called isorenieretane and related compounds, preserved in rocks from the late Permian shelves of China, Greenland, South Africa, Italy, and Oman. These biomarkers are a fingerprint that can only come from photosynthetic sulfur bacteria growing in the sunlit water. And they are everywhere. That is what makes the purple ocean real. It is not a poetic flourish. It is chemistry, written into stone, at multiple sites on multiple continents. At the height of the Great Dying, the surface of large portions of the world ocean was stained by the only organisms still thriving in it. Organisms that, in any healthier time, would have been pressed down into the dark and stayed there. And above that bruised surface, other things began to happen. Because hydrogen sulfide, unlike carbon dioxide, is a gas that does not stay dissolved in seawater easily once it crosses a threshold. When concentrations in surface water become high enough, it outgasses into the air. It rises, it enters the atmosphere. And once it is in the atmosphere, hydrogen sulfide has chemistry of its own. The modern atmosphere is protected from certain kinds of solar radiation by a fragile high-altitude layer of ozone. Stretching mostly between roughly 15 and 30 kilometers up, absorbs the shorter and more destructive wavelengths of ultraviolet light before they can reach the ground. Unfiltered UVB radiation would damage DNA in exposed organisms, kill phytoplankton in the upper ocean, and gradually break down the basis of most terrestrial food webs. Hydrogen sulfide, when it reaches the stratosphere in large quantities, reacts with the radicals that maintain ozone chemistry and contributes to ozone depletion. Models run by atmospheric chemists across the past 2 decades have suggested that sustained H2S flux from a strongly anoxic ocean could, over thousands of years, measurably thin the global ozone layer. Not a hole, not an abrupt collapse, a slow, sustained erosion. There is, in fact, direct evidence that something like this happened. In late Permian sediments, particularly in a handful of sections in Greenland, in the Arctic, in southern China, paleobotanists have found an unusual signal in preserved plant spores. Many of them are malformed. Their outer shells, known as sporopollenin, show the characteristic kind of damage produced by prolonged UVB exposure. The same kind of damage you can reproduce today by exposing modern spores to UVB in a laboratory. The mutation rate of land plants in the last thousands of years of the Permian appears to have risen sharply. And at the same time, the sediment record shows evidence of collapsing forests, a sharp decrease in woody plant debris, replaced temporarily by something called the fungal spike, a dramatic rise in fungal spores, as fungi fed on the enormous amount of decaying plant material produced by dying forests. The sky itself was failing, not all at once, not everywhere equally. But the protective veil of ozone was thinning. The sunlight reaching the ground was becoming, in places, slowly more dangerous, and the green layer of the continents was browning out from both heat and radiation. Imagine a slow, decade-by-decade reddening of summer skies as sulfur haze rose higher into the stratosphere. Imagine leaves, year after year, coming in smaller, more damaged, more mottled. Imagine a spring where the new seedlings do not quite form because their first unfurling cotyledons are scorched by light that was never supposed to reach them. Now, imagine that spring coming again, the next year, and the next year, and the next. For tens of thousands of years, the therapsids, the mammal-like reptiles that had dominated the continents, began to fail. Not in a single disaster, but in a cascade. Their vegetation base thinned, their climate warmed beyond the range their bodies could regulate. The complex ecosystems they had thrived in simplified. Species after species dropped out. In the deep stratigraphy of the Karoo Basin in South Africa, one of the best preserved terrestrial records of the PT boundary, you can walk upward through the rock and watch their world empty out, and in the sea, the loss accelerated. The reefs that had been stalled were now gone. Trilobites made their final appearance. Every last species, 400 million years of trilobite history, ended. The ammonoids lost perhaps 97% of their species in a single crisis, though the survivors would later explode again into the Triassic and beyond. The rugose and tabulate corals ended. The fusulinids ended. Entire orders, entire classes, entire family lineages that had persisted since the earliest Paleozoic were simply gone in a geological blink. It is worth stopping here, in the quiet middle of the story, to try to feel how long it took. 60,000 years. The word extinction, in common usage, implies speed. A single asteroid, a single winter, a single blow that comes and ends the world. The Great Dying was not that. The main extinction pulse of the end-Permian, according to the most carefully dated rock sections we have, unfolded across roughly 60,000 years. Some estimates, using higher resolution uranium-lead dating of zircons in the Mason ash beds, narrow the most intense phase to as little as 30,000 years. Others extend it, but the order of magnitude is the same, 60,000 years is longer than the entire history of our species' anatomically modern form. It is longer than our bodies have looked the way they look now. It is longer than agriculture and cities and writing and electricity and everything that has ever happened in what we call civilization, multiplied by many. If a trilobite in the late Permian had lived for 10,000 generations, the world that lived with it at its birth would be almost entirely gone by the end of its lineage, and the lineage would not yet have arrived at the true bottom. This is what the stone is telling us. The Great Dying was not a moment. It was a long, sustained, multi-generational reshaping of the entire biosphere. Every creature alive anywhere on Earth during that 60,000 years was, unknowingly, living through it. Every generation was slightly worse off than the one before. Every reef contracted a little further. Every forest came back a little thinner. Every anoxic zone reached a little higher up the shelf. The story of the extinction is not the story of a day. It is the story of a span of time long enough that whole successions of new organisms could evolve, try to cope with the changing world, and then themselves die. The deeper and deeper the anoxic water climbed, the more that was lost. In the shallowest, warmest tropical margins, where the reef systems had been richest, the losses approached totality. The coral-building organisms that had created the Great Permian reefs were gone. Reef architectures that had taken hundreds of millions of years to refine were erased, and when recognizable reefs appeared again, much later, they were built by different creatures entirely. Scleractinian corals, relatives of the ones that build the reefs of the modern tropics. But that recovery would not begin for a long time. For now, the shallows were barren. In the deeper water, patterns of kill were different, but the total was the same. Deep water species that had adapted across hundreds of millions of years to low oxygen, to steady temperatures, to the slow rain of organic material from above, found their world suddenly uninhabitable. Some of them persisted in small refugia, in places where local currents held back the sulfide, where cold water still sank fast enough to carry oxygen down. The vast majority of deep-sea life in the late Permian, by the end of the extinction, was chemistry. On the continents, the loss was slightly gentler in raw numbers, but it was still profound. Roughly 70% of terrestrial vertebrate species died out. Whole guilds of large herbivores and carnivores vanished. The therapside lineage that would eventually, through a long chain of survivors, produce mammals, nearly ended. It was held together, for a time, by a small, stocky, pig-like animal called Lystrosaurus, a plant-eating therapside that seems to have tolerated the low-oxygen, high CO2 world better than almost any of its relatives. After the extinction, in the earliest layers of the Triassic, Lystrosaurus is sometimes almost the only thing in the rock. Entire hillsides of fossils, mostly the same animal, a single species dominating the continents because almost nothing else survived. And then, slowly, the silence ended. Nothing about the end of the Great Dying was dramatic. There was no moment, no single year, no single generation where the world came back. What happened instead was simply that the pressure slowly lifted. The Siberian traps, after nearly 2 million years of pulsed eruption, began to quiet. The rate of carbon injection into the atmosphere slowed. The vast excess of dissolved carbon in the oceans across tens of thousands of years was gradually drawn down into sediments and weathering products and new minerals. The surface water began, fraction by fraction, to cool. And as it cooled, the polar sinking of cold water regained some of its strength, and the slow breath of the deep ocean came back, not quickly, not evenly, not to its former rhythm, but it returned. The chemocline, which had climbed into the sunlight, began to sink again. The purple sulfur bacteria retreated. The hydrogen sulfide stopped accumulating in the surface water. The atmosphere lost its sulfurous cast. The ozone layer, no longer under sustained chemical attack, rebuilt itself. and the UV stress on land began to ease. But the biosphere that had been there before was not the biosphere that came back. The earliest Triassic, the first few million years after the extinction, is sometimes described by geologists as the longest recovery in the fossil record. Complex ecosystems take time to rebuild. Reefs require the patient stacking of many species in cooperation. Food webs require predators with prey, and the prey require vegetation, and the vegetation requires soils, and soils require the slow action of tens of thousands of small organisms across centuries. None of these layers rebuild in a single human lifetime. Most of them, after the Great Dying, took millions of years. For perhaps 5 million years after the main extinction pulse, the oceans of the world remained what paleontologists sometimes call a disaster fauna. The same few species, found in rock after rock, across continent after continent, unusually small body sizes, an eerie simplified ecology. The deep water and tropical shelf environments that had been richest before were, for a long time, among the last to recover. There are stretches of early Triassic rock dating to millions of years after the boundary in which reef structures are simply missing. They do not come back. Something that had been continuously present in Earth's oceans for hundreds of millions of years on almost every shallow shelf was gone, and it stayed gone for long enough that if you had been alive, then you would have believed reefs never existed at all. But recovery, when it finally came, arrived not as restoration, but as reinvention. The scleractinian corals, the ancestors of our modern reef builders, appeared for the first time in the Middle Triassic, roughly 10 million years after the boundary. They were not the same as the Permian corals. They were a different group entirely, rising into the empty reef niche. The new ammonoids that filled the seas were descended from a handful of survivors that had been rare before the extinction, and now found themselves, suddenly, without competitors. The ecological roles that had been filled by trilobites, by fusilids, by rugose corals, were never filled by them again. They were filled by other things: crabs, lobsters, bony fish, gastropods in new shapes. The ocean that emerged across the Middle and Late Triassic was recognizably a modern ocean. Not in its geography. Pangaea was still whole, Panthalassa was still the world sea. But in its ecology, in its roster. The major groups of marine animals we are familiar with today, the ones that swim in our seas now, are, in large part, the descendants of those who came through the PT bottleneck. They inherited an emptied world, and they filled it. On the continents, the story went a similar way. The Therapsid lineage, which had nearly ended, was reduced to a small number of lines. One of them, over the course of the Triassic, would eventually, across tens of millions of years, produce the first small, shrew-like, warm-blooded creatures we recognize as early mammals. That lineage held on quietly, in the shadows of a new group of animals which had not existed before the Great Dying, and which would come to dominate the land for the next 160 million years, the archosaurs. The lineage that would split in time into crocodiles and birds, and into the group we call now the dinosaurs. This is the strange, uncomfortable truth of the Great Dying. Every major lineage of life on Earth today, including our own, descends from a survivor of it. The fish you see in any modern sea, your tuna, your salmon, your herring, your cod, all trace their lineage through the narrow bottleneck of those 60,000 years. The reptiles that sun themselves on modern rocks, the birds that pass overhead, the mammals that walk with you, the insects that survived in enough of their Permian diversity to explode again in the Triassic, the flowering plants that would, much later, reshape everything. All of them descend from organisms that, at the end of the Permian, were alive and continued to be alive, while 96 of every 100 marine creatures around them died. We are not the heirs of what was lost. We are the heirs of what got through. If you know where to go, you can stand at the boundary itself. In Maishan, in Zhejiang province in southern China, the PT boundary is exposed as a thin band of clay and ash between the gray limestones of the Permian and the recovery beds of the Triassic. It is protected now as a scientific monument. You can walk up to it, you can run your fingers along the layer. Beneath your hand is a seafloor, 252 million years old, holding in its upper microns the last signal of the old world, the last microfossils of species that would never be seen again. Above your hand, the new sediment of a dead sea, depauperate, empty, waiting for life to find a way back. There are other exposures. In Italy, in the Dolomites, in Iran, at Aberdeen, in Greenland, in East Spitsbergen, in the Karoo Basin of South Africa, in eastern Russia, in western Canada. Almost every continent has at least one section where, if the rocks were laid down at the right time and preserved in the right way, you can see the line. In some of these sections, you do not need a microscope. You can see it in the color of the stone. The Permian rocks are pale, full of shelly fossils, built by the countless hard parts of a living ocean. The Triassic rocks immediately above are darker, quieter, barren. There's a visible reduction in biological material, a visible thinning of the fossil record. It is written into the rock exactly the way you would expect, if you had only read about it, to be written. The geologists who work with these sections have a particular way of speaking about the boundary. They call it, almost always, simply the boundary. No further word is needed. If you hear a paleontologist say, this fossil is from below the boundary, they mean this creature lived in a world that ended. And if they say, this fossil is from above the boundary, they mean this creature or its ancestors somehow got through. What happened at the Permian-Triassic boundary is, in the ordinary working language of geology, a single crease. A catastrophe deep enough that the record itself goes strange. Carbon isotope swing, oxygen isotope swing, fossil diversity drops, trace fossil complexity collapses, and then, slowly, reassembles itself in a new key. And if we look across the deep time record of Earth, across more than 500 million years of animal life, it is easy to notice that the crease at the end of the Permian is the deepest in the entire book. There have been other mass extinctions. The end-Ordovician, roughly 445 million years ago, a much shorter crisis tied to sudden glaciation. The end-Devonian, in pulses through about 370 million years ago, reshaping the great early fish faunas. The end-Triassic, roughly 201 million years ago, which opened the stage for dinosaur dominance. The end-Cretaceous, 66 million years ago, the one we know best, the one driven, we are now certain, by an asteroid strike in what is now the Yucatan Peninsula, which ended the non-avian dinosaurs and opened the way for mammals. All of these events together are called the Big Five. Only one of them approached 96%. Only one of them hollowed the oceans to this depth. Only one of them changed the chemistry of the atmosphere and the chemistry of the sea simultaneously across tens of thousands of years at this scale. The Great Dying is, by every measurement we have, the single closest that complex life on Earth has ever come to ending. It did not end. And in the story of why it did not end, you can feel something close to gratitude. The ecosystems that came through were often hanging at their lowest points by thin lineage threads. A few small, tough, unremarkable animals, a few strains of surviving plants, a handful of corals, a single rodent-sized therapside in a dry upland. Poisoned, hot, oxygen-starved world, slightly better than everything around them. We are, each of us, downstream of those few. It is useful, sometimes, to reframe what is happening now in the light of what happened then. The Siberian traps released roughly 30,000 to 100,000 gigatons of carbon into the atmosphere. They did so across roughly 2 million years. The modern industrial age, in the span of about 250 years, has released roughly 2,000 gigatons of fossil carbon. That is less than a tenth of the total volcanic output of the traps. But the rate per year of modern carbon release is significantly higher than the rate of the traps. We are not yet in Permian territory in terms of total emissions, but we are entering it by some measures in terms of speed. The oceans are warming. The oceans are losing oxygen. Oceanographers now track globally an ongoing expansion of zones in the modern sea in which oxygen concentrations are dropping. These are still small compared to Permian anoxia. They are also worth paying attention to. None of this is meant as alarm. It is not the work of a sleep documentary to raise alarm. It is only meant as a way to feel the story. To understand that what happened at the end of the Permian was not something exotic. It was the ordinary chemistry of a warming atmosphere and a slowing ocean, taken to its extreme across enough time. The mechanisms are not strange to us. We already know them. We study them on smaller scales every day. What is strange about the end of the Permian is not the chemistry. What is strange is how much was lost. This is where the story, in its deep time frame, grows very quiet. 252 million years is a long time. It is long enough that the very geography of the Earth, at the moment of the Great Dying, is gone. Pangaea has broken up. Panthalassa, the world sea, has fragmented into our modern oceans, each with its own name and its own current systems. The Siberian traps still exist as a weathered volcanic province in central Russia, but they are no longer smoking. The Meishan boundary layer still exists as a fragile band of clay beneath a ridge in a village in Zhejiang province, but the sea it was laid down in is gone, and what is there now is a quiet hillside. Everything the Permian oceans contained, the trilobites, the fusselinids, the rugose corals, the sea lilies in their great pastures, the coiled ammonoids in their millions, all of it is gone, except in stone. Their descendants, where they have descendants, are hidden inside shapes that look almost entirely different. Their direct lineages, for the most part, ended. And yet, if you listen carefully, the story is not only one of loss, because nothing in Earth's record ever truly starts from nothing. Every recovery is built from the survivors. Every new ecosystem is a reinterpretation of an older one. Every coral reef, every kelp forest, every schooling fish, every nest of birds in a morning tree, each of these is a distant, patient continuation of an unbroken thread that, at a certain unremarkable-looking layer of mudstone in southern China, came within 4% of breaking. The ocean now, if you stand on any shore, is quieter in some ways than it was in the late Permian. It is less crowded with ancient shelly creatures, but it is also, in ways that matter, exactly as alive. The light that reaches the surface water today feeds algae that feed the same kind of web in shape, if not in species, that fed the Permian. The bacteria in the sediment are, in many cases, direct descendants of the ones that were there then. The cycles of nitrogen and sulfur and phosphorus run on. The long, slow breath of the deep ocean continues. And if you could, somehow, put a buoy in the middle of any of our current seas and listen for long enough, you would hear, not in sound, but in the way the water moves, the continuation of something that came very close to silence once and did not. The Great Dying is not a story that teaches a lesson. It is too large for that. It is simply a record. It says, in the voice of the stone, that Earth has lived through worse than anything we have ever seen, and has done so without any outside agency, and has come back, and has filled itself again, and has produced, eventually, creatures capable of standing over a layer of clay in a Chinese village, and understanding what it means. The purple seas have been gone for a very long time. The breath of the ocean has returned, and the world, which we often forget is old, is still here, still breathing, still patient, still riding its slow chemistry into the stone beneath our feet.